Ooh, right off the bat, this video is already riveting. Yeah. I only made that joke because I knew you were all going to. Yeah, I read your comments. I know what you did. Hello, Internet. My name is Quinn, and this is Blondihacks. I've got a tool build for you this week. I'm going to make an embossing tool for my drill press. It's going to involve a fixture that's adjustable with a fence for aligning the embossing work to the sheet metal, and then there's going to be a hardened tool and die set for embossing the work. In my case, I'm going to be making rivet details for a model, but you could use this for all sorts of different embossing types of tooling. So hopefully you'll find something useful in here. Let's go. This tool will make more sense if I show you the effect that I'm trying to achieve. Here is a typical steam locomotive, and if you look closely at one of these, let's zoom in on the tender back here, you'll see that the bodywork on them is made up of many panels that are riveted together. And if you're trying to build a model of a locomotive like this, you really want to be able to replicate that riveted panel effect. So my embossing tool is going to be kind of like a punch that's going to create surface bumps that look like rivets at this scale. Here's another view that might make it more clear. Sorry, these are old photos that aren't very well preserved, but you can see how the back slope of the tender is made up of these riveted panels. And that look is very much characteristic of a steam locomotive. Here's the tool that I've designed to hopefully do this. It's a pretty straightforward hardened steel punch with a hardened steel die that sits inside a base plate that has an adjustable fence on it. That will hopefully allow me to get really consistent rows of rivets along a panel that I'm making. Drawings and 3D models of this are available on my Patreon as usual if you're interested. I'm going to start with the punch and die. For that I have this 01 tool steel drill rod. It does need to be tool steel because we're going to be heat treating it. I'm going to cut a length of it that's more manageable over on the bandsaw and set it up in my lathe for some turning. Drill rod is awesome for quick tool making projects like this because it comes softened so you can machine it, but it's easily heat treatable, and the OD of it is precision ground so you have an excellent surface finish and it's right on dimension. I'll make the die first. This is center drilled and then drilled with a drill that is the same size as the rivet heads that I want to create. The edges of this hole are what are going to actually create the outer diameter of the rivet. The depth isn't super important, it just needs to be deeper than the height of the rivet heads that I want to create. But not too deep that it goes all the way through the die. Although I guess really it doesn't matter if the hole goes all the way through the die. Now I'm ready to part this off. I'm parting it off over length, and I'll be facing it down to final length later to ensure an accurate length. Accurate length is quite important for this die once you see how it's installed. And Yahtzee. Now I'm going to leave the stock in there and face off the detritus from parting because I'm going to make the punch right in this same setup without even moving the stock. The reason is that the tip of the punch is a very, very small diameter. When you need to turn really small diameters over long lengths, this is a way to do that. You work on the piece in sections so that for each feature, only the amount of material that you absolutely have to have out of the chuck is out of the chuck. The tip of this tool is strong enough to support its own length for machining, but you wouldn't want any more of the stock sticking out for the rest of the features on this yet. Once I've got the radius correct for the tip, then I can start worrying about the radius on the end. It needs to have a ball nose end on it because it needs to create a round or a dome-headed rivet. I'm going to do that with a file because this piece is really too small to try and get out the ball turning tool or anything like that. So a little bit of trial and error with a file and checking with the radius gauge should get me there. The radius that I'm aiming for is 15 thousandths, which is really too small for me to see by eye, but a little bit of magnification and my 15 thousandths radius gauge, and I can sneak up on this radius. Just checking and filing, going carefully until I get there. That radius is actually a little bit smaller than the shank of this point, so I'm going to create a little taper to blend those two together, also with the file. Doing that simply by eye, and then I verify again with the radius gauge to make sure I haven't borked up my radius in the process of doing that. I'm using a little bit of emery as I go to keep everything nice and shiny and keep the surfaces blended together. Now I can pull the piece out a little bit and work on the next section. So you can see the technique in action. You work your way back on the tool, working on each section so that you're always working very close to the chuck and you don't have a lot of stick out on any of these thin features. This next feature is a taper, so I've set my compound around to something that looks about right, roughly 45 degrees. This will transition the main body of the tool into the tiny pointer area. This operation is a basic taper cut with the compound, nothing too tricky here. There's nothing critical here dimensionally, it just looks nice and also makes the tip stronger because we're eliminating sharp inside corners where stress would tend to concentrate and potentially break off the tip. The taper here also makes it easier to see what you're doing when you're using the tool. One thing to note about this technique of working backwards in sections on a small part is that you do potentially lose concentricity doing this. Each time I pull it out of the chuck a little bit to work on the next section, you've lost some amount of concentricity versus the sections that you turned earlier. Now, this being a collet chuck, that difference is minimal, and this isn't a spinning tool, this is a stationary punch, so concentricity is not that critical. If this was really critical for concentricity, something like a spinning shaft, then you might have to do this in a single setup with a steady rest and moving the steady rest back instead of moving the stock out in the chuck as you work. With the business end done though, I can flip the piece around and I'm going to part it off to length. This tool is going to be used in my drill press, so I've attempted to calculate the length such that it will bottom out in the Jacobs chuck on my drill press. This is a pressing tool and I don't want to have to rely on the jaws of the chuck to hold the tool in position. I want the base of the chuck to be pushing on the end of the tool. And Yahtzee. And finally I can face this end and put a nice decorative chamfer on the end as well with a file. That's why I flipped the piece around so that I could do the facing and the chamfering in the same setup rather than just pulling the piece out and then parting it off. Alright, that should be the machining work done on the punch. Now I'm going to move back to the die, which is mostly finished, but I need to stick it back in the collet chuck and face it down to final length. Collet chucks are great for holding tiny parts like this. I have to start by facing that smooth, get rid of all the parting blade detritus, and then I can take it out again, measure the current length, and determine how much I need to face off to get it down to final length. You have to do this in this order because otherwise you're trying to measure an unmachined surface for your final cut and you'll never get an accurate length doing that. This length needs to be accurate so that it'll sit flush in the base of the tool and woof, man, dead nuts. Gotta like that. Okay, that's probably a couple tenths over, but that's good enough for this. Now over to the hearth for heat treating. Heat treating is a very complex topic with a lot of very strong opinions, let's say, but this is a very simple tool and I'm going to be heat treating in a very simple way. All you need is a torch and a little bit of practice to do this. Start by heating the thing up to a glowing orangish red, then quench that in oil because this is oil hardening steel. I'm using canola oil for this because it smells like French fries, and then I'm going to do the same thing with the dye. This step is pretty foolproof as long as you've seen that steel glowing orangish red for a couple of seconds and you quench it immediately in the right liquid, it'll harden. And this is the hardening step. It's now very hard. Too hard, in fact. At this point, the steel will be brittle, so we need to temper it and give it a little bit of flexibility. For this, the material has to be clean and have a good surface finish so that we can see the color of the steel. That's very important on this step. To temper the piece, I heat it from the far end, not the business end of the tool, but the far end, and I do this very carefully and slowly, not too much heat. You don't need very much for this step. And I'm watching the color creep down the end of the tool. You'll see a yellow and then a brown, then a blue and a purple. And you want to stop when that yellow color, as it creeps down the end of the tool, you want that yellow color to just reach the tip of the tool and then stop. Now the trick here is that heat has inertia. So you need to stop tempering a little bit sooner than you think you should and then immediately quench the part in water. Now this quench does not harden anything, this just stops the tempering process. It puts the brakes on that heat inertia. This is the same reason that you rest meat after cooking it, because it keeps cooking after you take it out of the oven. Tempering steel has the same effect. The process is the same for the dye, but because I don't have that long length, I have to kind of just kiss it with the torch and wait a minute, and then hit it again and wait, and just watch that color develop in it, and again, try to stop on that light yellow color. Here's the final temper. Now, I ended up with more of a brown than a yellow on the end, so this is probably a little bit over-tempered. but we're going to try it anyway. Then you can see how the brown turns into purples and blues, and those purples and blues are softer and softer tempers. The technique that I demonstrated of tempering from the far end is in fact how tools like this are typically tempered, even in factories. The reason being you want the shank of a tool like this to be softer than the end. You want the shaft to be a little bit flexible so that it doesn't break when you're leaning and twisting and torquing on it, but you want the business end to be very hard so that it holds its shape. So twist drills, screwdrivers, chisels, files, things like that are typically tempered from the tang or shaft end down towards the business end. You can see the die ended up pretty brown as well, so that's probably also slightly over-tempered. It's not a big deal for the die, which doesn't actually need to be that hard. The punch, however, I may have trouble with that, but we'll see. This is that heat inertia effect that I talked about. It's very, very easy to over-temper. And I know people are going to comment with a million different methods that they have for tempering that they are going to say are better. And yes, you can use fancy ovens and lots of different ways to do this, but the point is you don't have to. A little bit of practice and a $5 torch really is all you need to heat treat your own tools. Onto the base of the fixture now, I'm going to use this stuff. This is 1/4 inch aluminum gauge plate. You can buy this from tool suppliers. It's Blanchard ground on both sides, and that means it's very, very flat and very, very parallel. So flat and parallel, in fact, that the pieces will almost ring together like gauge blocks. Not quite, but they do get quite sticky in proximity to each other. Pretty cool. Now this stuff's not cheap, but what's cool about it is that it saves you immense amounts of time on tool and fixture making projects like this. What this stuff means is that you don't have to go through all the rigmarole of squaring up stock, which is quite an elaborate and time-consuming process, especially on large flat surfaces like this, where squaring up requires a lot of tool changes and other effort. I sized my fixture such that I could get both pieces out of one of these chunks of gauge plate that you can buy from McMaster, and I'm going to split this in half with the bandsaw and then do some machining from here. And here's the superpower of gauge plate. I can stick it straight in the vise, no copper wire, no rigmarole to maintain parallel or squareness. Just clamp it straight up like this, and then machine one edge, and flip it over, machine the other edge, and you've automatically got 4 straight, parallel, and square edges right off the bat. Very little effort. Because these two Blanchard ground sides are parallel and flat, we don't need additional references in order to create square edges all the way around. That's really a huge, huge time saver. So as I said, machine that one edge, then deburr that. Now flip the part around and I can put that machined edge down in the vise and machine the new top edge. And I'm going to end up with 2 edges that are parallel to each other and are both going to be square to the large ground surfaces. So 2 quick cuts, and now I can put the piece flat on my parallels like this and do all the rest of my operations from this single setup. I really do love this stuff. I can start by side milling both ends to get them straight, parallel, and square and get the overall piece down to final length. Again, doing all this from one setup conveniently because the piece is wider than my vise, makes it super easy. Then I can edge find on one corner and do all of my features from this single setup. This is the bottom piece, which just needs a couple of threaded holes in the corners. These hold the sliding fence in place. Because there will be a piece sliding over this, I want to make very sure that there's no burrs or anything on these threaded holes, so I'll use the chamfering tool, put a nice little chamfer on there. Now over towards the middle, I'm going to make the hole that holds the die. This is mostly a blind hole, but it has a little tiny hole that goes all the way through. This is going to act as a pilot for the other operations, but also it leaves me with an air hole and a paperclip hole for getting the die out if it gets stuck and for preventing air piston effects when you're trying to put the die in. Next, I'm going to drill a little bit undersize with a square ground drill. This is a DeWalt pilot point drill. I've talked about these a lot. They have square shoulders on them, so they create almost perfectly square bottomed holes, minus the little pilot point that they have on them. That drill left me with mostly a square shoulder in the bottom, but also removed most of the material so that I can now plunge with an end mill of the diameter that I want. And the end mill isn't doing very much work, and that means it's going to tend to cut on size. If you just plunge straight in with an end mill, you tend to get an oversized hole because end mills don't have anything to keep them on track and guide them like a twist drill does. So the cutting forces are going to tend to make the end mill deflect a little bit and cut oversize. Moment of truth, let's see if my die fits in the hole. The answer is, no it doesn't. And well, this was probably to be expected. The hole is on size, but the die is actually slightly oversized. When I made this die, it was about half a thou under nominal, which should have made a very nice sliding fit into that hole. But since heat treating it, it's now about half a thou oversized. So it expanded a little bit in the heat treat, which is typical. That's why if you're making precision tooling like gauge blocks and 123 blocks, you machine them a little bit oversized, then heat treat them, and then surface grind them to final dimension. However, here in the poor person's shop, we can just hit it with the Scotch-Brite a little bit and bring that down to dimension. This doesn't have to be absolutely perfectly round again, it just has to be a nice fit in that hole. The amount that it expanded from the heat treat is well within Scotch-Brite polishing range. Quick kiss with the Scotch-Brite wheel, and now that is a perfect fit. Look at that. Delightful. Quick test drive of the paperclip hole. Result. On to the sliding fence now. I'm going to start by drilling the ends of the slots for this piece because the dimension of the slot that I want is a bit of an odd size. It's a close sliding fit on the bolts, which means it's not a standard end mill size. I'll show you a trick for getting a good result anyway. For the milling, I'm going to try this stuff for the first time. This is A9 aluminum cutting fluid. A viewer sent me this. He said it's just the stuff for aluminum, so I'll give it a try. My usual cutting fluid for aluminum and brass is WD-40, which works okay. It's a little bit messy, so let's give this stuff a try. The end mill I'm using is smaller in diameter than the holes and smaller than I want the final slot to be. So I'm going to work my way down the center of the slot with this undersized end mill. I did this in a few passes because it's a fairly small diameter end mill, although to be honest this is aluminum. I probably could have done it in one pass, but I was being conservative. Wasn't in the mood to break an end mill today. With that center pass done, now here's the trick. I put the end mill back on center on one of the holes, so the end mill is smaller than that hole, remember, and I feed the table sideways until I hear the end mill touch off on the side of that larger hole. Then I feed down. So now I'm widening the slot and creating a surface that's tangent to those larger end holes. So the ends of my slot remain round, but I've managed to widen the slot with an end mill that's a smaller radius than the final slot is supposed to have. This is a little bit nicer than, say, simply doing 3 passes to get the width of slot that you want with a smaller end mill, but then you'll end up with slightly squared up ends on the slot. Whether that matters or not is up to you, I guess. I'll do a test fit now with the other piece, and that looks really good. The slots line up, the edges line up, slot moves nicely, so I think this is a result. Once again, since these parts are sliding against each other, I will chamfer this slot. This is actually the underside of this piece that we're looking at. So I go down one end with the chamfering tool centered on the hole, and then feed the table down, chamfering the edges as I go. This is a nice trick with a chamfering tool to chamfer a complex feature like a slot. If you center the tool on the slot, it works very, very well like this. You get a really nice chamfer all the way around. If you're a little off-center because you read the DRO incorrectly, well, then you end up with a chamfer that's a little thinner on one side than on the other. I guess I won't win the Academy Award for toolmaking this year, but those awards are all political anyway. Test assembly now. Let's see if this thing has any chance of working. Well, it certainly looks the part. Get the die in there and, well, okay. It seems like it might work. Let's get it over to the drill press and find out. Sorry, Float Lock Vise. I love you, but you won't be of use here, so you need to go take a nap for a while. I'll get the fixture in here, and step 1 is to align the die with the spindle of the drill press. To do that, I'm going to use the drill that was used to make the hole in the die. I'm going to put that in the chuck upside down so that I've got the shank of the drill, and I'm going to use it as a kind of a workaday gauge pin, if you like. I line up the fixture on that drill. Once that's sliding down in there nicely, I can lock the quill, and that'll hold it in position while I do the rest of the setup. The next step then is to get the distance of the fence correct to the hole. This doesn't have to be super accurate, but eyeball and scale should be good enough for that. Then I lock down the fence, then clamp the whole fixture down to the table. This step is a little bit clunky. It would be probably better if the base was wider to give me clamping surface that would still allow me to move the fence independently, so make a note of that for future improvement. Now I can swap out the drill for the punch tool. Unfortunately, I apparently measured wrong and the punch is a little too short to bottom out inside the drill chuck. I clamped it down real hard and maybe that'll still work. Okay, I've got a piece of brass to test this out with. This has been annealed, so it's pretty soft. And let's give it a whirl. Here goes. Punch number 1. Oop, yeah. Immediately the tool slid in the Jacob's chuck. So I got a little bit of a rivet embossing there, but yeah, that is not deep enough and the tool clearly is going to slide in the jaws. So I need to do something about that. Rather than remake the tool, I made a little packing block of sorts from a scrap of drill rod that'll bottom out in the chuck and allow the base of the inside of the Jacob's chuck to be pressing on the back of my punch tool. And lined up on that rivet again, and I'll deepen it a little bit. And, yeah, that almost worked. I got a nice deep rivet. However, I bent my Wookiee. I was worried about the temper being too soft on the point of that tool, and it looks like I was right. I hate being right about stuff like that. The rivet, however, turned out great. It's got nice vertical sides on it and a dome sitting on top of those. Really nice and pronounced. It's beautiful. So I want that result. I just need the tool to be a little tougher so it can work for a living. I'll start by straightening it out. I can do this by eye. Again, this isn't a spinning tool or something that requires absolute perfect concentricity or straightness, so if it's straight by eye, that's good enough. So a couple of tweaks in the vise and it's straight once again. Once it's straight, all I had to do was take it over to the hearth, harden it again, and temper it again. Because this is steel and steel is awesome, nothing is permanent. You can just redo the heat treat until you get the result you want. This is what I should have done the first time. You see how I've got a nice light yellow at the tip now. I stopped sooner this time. Like I said, there's a little bit of skill in this process, but I stopped sooner and I got a nice light yellow. You can see side by side here how much more yellow and less brown it is than the first time. I didn't bother redoing the die because again, the die doesn't need to be that hard. Now it's time to refine the process of using the tool. Tool development is as much about process development as it is developing the actual tool. And I wanted a way to get a good consistent rivet pattern on a panel. I decided to try doing that by laying it out on my computer using Affinity Designer or whatever drawing software you like and printing it out, and then I'm going to spray glue the pattern to the panel. And this way I can ensure hopefully a nice consistent pattern where there's a rivet in each corner and the spacing is all really even and so on. So it'll look like someone actually riveted this with intent. Let's give this a whirl. The template seems to be a big help. Obviously I'm not being perfect here with my alignment, but it's definitely helping. And the new temper on the tool is excellent. Quinn from the future here cutting in to say, I've since done many thousands of rivets with this tool and it's held up great. So a little bit harder temper is all it needed. Because someone's going to ask, why didn't I just create a registration hole that's the right distance away from the die hole, such that you could register the previous rivet in it, and then create the next rivet the correct spacing automatically? That's an interesting idea that I also thought about. The problem with that is that error in that scenario is cumulative. If you misalign one rivet slightly on the registration hole, then every rivet after that is going to be off. An error is going to accumulate to where you get to the other end of the panel and you might be completely off. Whereas with a paper template like this, it's a global pattern, so any error on a specific rivet is confined to that rivet and won't mess up the overall pattern. If you're wondering about doing this on the mill and using the DRO to space the rivets, you could, I suppose. I don't want to abuse the quill on my mill like that. My drill press is a lot tougher. That went pretty well, but some more learnings here. First, the panel got quite bent, and that's because there's no clearance vertically around the die for adjacent rivets. So as I'm riveting, adjacent rivets are causing the panel to bend. I also learned not to try and clean up the panel on the Scotch-Brite wheel because it's too aggressive and it flattened all of my rivets. So I'm cleaning it up by hand, and valuable lesson learned there. So this panel turned out okay, but still room for improvement. The one rivet that's cattywampus was the initial test rivet. The rest of them were done with the paper pattern. The next improvement I want to make then is to create some clearance around the die for adjacent rivets so that the panel doesn't end up curved like that. You could also make the die a little taller, but I've already made the die and I've heat treated it and everything. I don't really want to do that again, so it felt easier to simply machine a clearance around the die working area. Not too deep here. If I go too deep, then the material is going to slide under the fence, and I don't want that. I want just enough clearance for the rivet heads. I also learned that it might be valuable to have a semicircular clearance cut out around the die for the punch tool. If you're trying to punch rivets really close to the edge of the material, then the punch tool runs into the fence. So that clearance should help. All right, I've got another annealed piece of test brass. This time I'm trying taping a scale to the piece as a way to space out the rivets rather than the paper template. This actually worked okay too. If you're doing a really simple straight line of rivets, I think this is probably faster than setting up the computer. I also learned that I really hate the depth stop on my drill press. The depth stop ensures that all the rivets look the same, but these double nut style depth stops on cheap drill presses are really annoying, so that might be a future upgrade for this tool. I gotta say though, the tool is really feeling dialed in now. I'm getting really consistent, smooth results. I can go quite quickly. The tool is performing great. The rivets are all coming out very, very consistent. Really, really pleased with this. And again, if you keep them away from the Scotch-Brite wheel, they come out really, really nice. Very nice dome shape, a little bit of vertical side all the way around them. The piece stayed flat, so that clearance that I milled really helped. Everything seems to be dialed in now. Very pleased with that. If I do another round of improvements on this tool, it'll definitely be on the clamping system. As I said, it's very fussy to set up because the clamps have to go down on top of the fence, and so you have to set the fence and the spindle alignment kind of at the same time, but you wish you could do them separately. So if the base was wider and gave me somewhere to clamp independently of the fence, or maybe if there were countersunk bolts on the base that would allow me to clamp to the T-slots, something like that, I'm sure there's various ways you could make the clamping system better. That would be definitely an avenue for improvement here. But this tool is working really well. It's getting me the results that I want. So I'm going to go ahead and use it as is for now. I hope you've enjoyed this process and maybe you've learned something here that you can use on your own tool making projects. Thank you very much for watching. Thanks to my patrons for making all of this possible and keeping this content ad-free. And I will see you next time.